Hi, everybody, and thanks for joining us. We're here today with Ron Green from Intel. Ron, welcome.
Oh, thank you. Yeah, it's good to be here.
Ron, you spend a lot of time these days, I've noticed, talking about vectorization.
Right.
Why is that so important in parallel programming?
Well, for many years we've been talking to customers about parallel programming, but we've been talking about it in the context of cores. So, obviously we start out with dual core systems and then quad core and, 8 cores. So the cores have been increasing and people have known this, right? And also the number of sockets we put on servers have gone from 1 socket to 2 socket, 4 sockets. So the servers have been increasing in core count. So people have been aware probably for the last 5 or 6 years that, hey, it's really time to look at parallelization and getting these codes to scale is one of the terms we use, and to scale efficiently. Mm-hmm. But one of the other things that's been going on kind of quietly under the curtains that maybe people weren't paying attention to was internal parallelism within the processor. Hmm. And so what's been happening is with the modern processors, we have data parallel registers within the processors that can hold multiple elements of arrays or vectors or data. So let's say you have 4 data items. You can take these 4 data items, load them into a fat register, and then have 4 other data items and add them together, multiply them, and you can do that in 1 clock cycle. So you're effectively getting parallelization internally to the processor. Now, this has been around for a while. We've had this since Pentium 4 days, maybe even back to the Pentium 3 days, so it goes back a long ways. But what's happened recently, within the last 2 years, is that we're starting to increase the size of these registers. So they started out at 128 bits. Mm-hmm. So in single precision, floating point values or 32-byte integers, you could put 4 of them in there. Well, now, with the modern processors that are out today and have been out for 3 years, the Sandy Bridge and the Ivy Bridge, we doubled that. Mm-hmm. So now you've got 8 data elements that you can do in parallel. And with our Intel Xeon Phi coprocessor that we just released, we doubled it again. So now you can have either 16 32-bit data elements done in parallel or 8 double precision done in parallel. So before, it wasn't such a big deal because if you weren't vectorizing and taking advantage, vectorization is a term we use to taking processing of data and to break it into chunks and to do these chunks within these large fat data registers internally. Mm-hmm. If you weren't doing that before, you were maybe leaving 2x or 4x on the table. You weren't getting the performance that you wanted out of the processor, but it was only 2x, 4x. Well, with Intel Xeon Phi, now you're looking at 8x or 16x of your theoretical peak that you're just leaving on the table if you're not vectorizing. So cores are still important. You still have to scale, but there's this internal parallelism that you have to exploit also to get the most advantage out of modern processors.
So what discipline does a programmer need these days to be able to take advantage of the extra power?
Right. So the extra power, there's a couple ways you can take advantage of it. And one way is to let the compiler do it, and that's what we call automatic vectorization. And the compilers these days are smart enough to look at your data patterns and typically inside of your loops, your iteration structures, and to see the data that you're bringing in and to pack it into those registers and do things automatically for you. And in most cases, the compiler can do that. But when the code starts to get complicated, the compiler can't figure out how to quite do that. So then you have to kind of switch and throw the onus on the programmer to do something we call explicit vector programming, which is either pragmas or directives to help guide the compiler and say, hey, within this loop structure, I really want you to vectorize this region. I want you to pack the data into these data registers and do these operations in parallel. And in order to do that, you have to have some information that, it's safe to do this because there are loop carry dependencies and other programming things you have to be aware of that could cause problems. But if you're sure that it's in there, you can guide the compiler and help the compiler because no compiler is perfect today.
Your colleague, Gary Carlton, has an interesting phrase or an interesting call that he's issued on a couple of the interviews we've done with him that because of all the new power available to programmers, that developers need to rethink their relationship to compilers.
Absolutely.
Which I think is a great way of putting it. It's
right.
What has worked in the past, how you traditionally think about it, really no longer applies.
Right.
Would you agree with that?
I would agree with that. In the past, you could take your program and you could give it to the compiler and it would do the right thing in most cases. There were some cases, of course, nothing's perfect, but it was much simpler. because you weren't trying to exploit this internal parallelism of the processor. There wasn't any internal parallelism, right? So it didn't have to parallelize the code. It didn't have to vectorize the code to do data parallel operations. So they were simpler compilers. The programmer didn't have to worry as much about it. Compiler technologies has come a long way, but now programmers have to realize they have to have a relationship with their compiler and to help guide it and coax it and kind of you know, give it a little prod and say, I really want to do it this way. You know, take my word for it. In other words, you know, I know what I'm doing. Here's my code. Here's how I want you to compile it.
To be a more active partner.
To be a more active partner in a relationship. Well, it's kind of weird to say you were in a relationship with a software program, but in essence you are if you want to get the most performance out of your code.
Because we've got a mix of folks in the Go Parallel audience, people just joining the parallel community and people who've been with you since the start. Let's tackle this as we usually do on two fronts. So one, tell us a little bit about the purpose of the tool, in this case Advisor, for the newbies, and then for folks who've been with you a while, what's new for 2013?
Okay. Well, the Parallel Advisor is something I'm pretty excited about. When I first heard about this tool, the idea, well, let's back up a bit. The idea with Parallel Advisor is you have a code that's currently running serial, and you know, how would I transform this code into something that can exploit all of the multi-core architectures in a parallel fashion? So how do I parallelize this code? And as a programmer, you know, a former programmer, I guess I'm still a programmer, the temptation is just to dive in and start coding. Now the problem with that is you're hacking up your code. It's no longer going to pass a regression suite because you've been modifying the code, you've been actually making changes to the code, and you're also operating blindly. You don't know what you're going to do. You don't know what the end result's going to be. You think you know. You say, well, I'm going to parallelize this region because I know there's a lot of time spent here, but you really, a couple things you don't know. Is it going to work? Is it going to work correctly? And what is my expectations for the entire application? You know, certainly we can parallelize this region and we can get a scaling study and say, wow, you know, I got a 8x speed up in this region. What's the impact on the whole code, right? So Advisor allows you to run a couple of things. It allows you to run experiments. So you find first off, it finds the parallel, where you're spending time in your code, the target spots, the hot spots for the parallelization. The next thing it allows you to do is, without modifying the code, you annotate the code with special pragmas or function calls to say, this is where I'm thinking about parallelizing. I'd like to parallelize in this region. And within this region, here's a task or a work bundle that can be possibly done in parallel. All right. Now this is an experiment, and you run this code, and it'll tell you in a graphical form, you know, with reds and greens and yellows. The red is bad, green is good, yellow's kind of in between. How much is this? You know, how much scaling am I going to get from this parallel region? But not only that, it rolls up the statistics for the entire program to say, you know, hey, this is going to give you an 8x, or this is going to give you a 2x. It sets your expectations properly for the end result of the code. So that's one part of it, is to actually try this experimentation without, you know, going in and wholesale hacking up your code with actual parallelization, wasting a lot of time doing it. And the next phase about this is, it's great to say, I want this to run parallel. But, yeah, and if that was the case, you could just go up to the main program and take everything from the begin to the end and just say, parallelize it. I want to parallelize this whole thing. The trouble is there's dependencies and variables that could be modified by multiple simultaneously running threads or tasks, and those are called race conditions. So there's correctness. Correctness is essential. So yes, you have to parallelize, but it has to be correct. So you don't have any of these hidden bugs that are going to crop up in your code, and they may be runtime bugs that you may not catch all the time. So another key feature of Advisor is to run through the code and define these race conditions and these errors where you need to protect variables or move the scope of the variables so that you get local copies on each parallel task so that they're not sharing data. So
is Advisor primarily a tool for converting existing code into parallel, or does it have utility for greenfield parallel code as well?
Well, it can do serial code, certainly, because that's what it's designed for, is to kind of let you start to experiment. But if you have an existing parallel code, you can, you know, obviously run it on one thread or one process just to see, you know, pretend that it's serial. You can also annotate around your existing parallel regions so that you can model them. And there may be other regions that you haven't touched. So the analysis of the runtime to find those hotspots, if you find a hotspot you haven't parallelized, you can use this tool to see what the impact of parallelizing that additional hotspot region.
Makes sense. So it's like with people who are car tuners. If you add certain souped up features to your engine, you want to make sure your transmission can handle it.
Absolutely.
So that's the basic functionality. What's new this year in all of what you just described?
Let's see. So what's new this year is the, well, in Composer XE 2013, so I'm going to switch gears from Advisor because we just talked about that. Let's talk about the compiler. The compiler has support for the Intel Xeon Phi, which is a big deal, right? So that's, the hot topic of the day. We have extensions, pragmas, and directives that people can use in their code to help offload parallel regions to the Xeon Phi coprocessor. We also have something called a native mode where you can compile code to run just natively, just run the code on the Intel Xeon Phi. So that took a lot of work. We just talked about it in 1 minute. Easy to say, but it was actually quite a bit of work to get the compiler to do that properly.